In this lecture, let us discuss about logical semantics. Logical semantics in natural language processing involves representing the meaning of natural language expressions using formal logic. This approach enables machines to reason about language, infer meanings, and ensure consistency in understanding. So, it mainly helps us in understanding how words, phrases, and sentences contribute to meaning, enabling computational systems and linguistic theories in order to process human language systematically. Coming to the fundamental concepts, the first one is truth conditional semantics. Truth conditional semantics is an approach to understand meaning in natural language based on conditions under which a sentence is true or false. So, here meaning is understood in terms of conditions. For example, if you take a sentence, the sky is blue, it means that the sky is blue under specific conditions. Say if the sky is indeed blue, then we can say that the sentence is true. For example, if the sky is not blue, then we say that the sentence is false. Second one is compositionality. This principle states that the sentence could be understood by breaking it down into smaller components such as individual words or phrases and analyzing how these components combine. So here meaning of sentence is determined by the meaning of individual words as well as the grammatical structure that binds them together. Meaning of complex expressions is derived step by step, starting with the basic meanings of words and building up the meaning of larger structures. Say, if you take this sentence, every student reads a book. So, here first, this word every, it is a universal quantifier, which means all. And the second word student, it refers to set of individuals. Then reads, it is a predicate which takes a subject and an object. Then a book, it refers to a book. So, like that, the complex expression will be broken down or divided into multiple steps. So, starting with the basic meaning of the words, so we'll take the basic meaning of every word and build up the meaning of this complete sentence. So, here the meaning of the sentence can be composed like this. So, this is a formal representation of how the individual meanings combine to produce the meaning of the entire sentence. Let us see few examples. Say if it is a simple sentence, first we need to find out meaning of every word present in the sentence. So we are taking two words separately. So here John is a person, whereas sleeps is nothing but action of sleeping. So compositionality means here we need to combine meanings of both John and sleeps in order to form the sentence meaning. Then, if you take a complex sentence, the dog chased the cat. So, take the individual words dog, cat, chased. So, here dog is nothing but a specific dog, cat again, specific cat, chased is action of chasing. So, now we need to combine meaning of the word the dog with other words chased and the cat in order to get the complete meaning of a sentence. Then predicate logic, which is also known as first order logic or FOL. So this is a formal system used in logical semantics to represent the meaning of natural language sentences. It provides a structured way to represent the relationship between entities and properties in a sentence. Then the core components of this predicate logic are predicates, arguments, quantifiers, and logical connectives. We can say that the predicate is a function that takes one or more arguments and returns a truth value, which is either true or false. And the arguments typically represent entities in the domain of discourse, like individuals, objects, or locations. So, this is the general form of a predicate logic expression, which is having multiple arguments like this. So, example is you can write it like this: predicate, so predicate is loves and arguments are John, Mary. So meaning is John loves Mary. So let us see few examples in predicate logic. First we need to break down the sentence into simple units like subjects, verbs and objects. Say if you take an example, John is a student. First, we need to break down the sentence into multiple parts or simple units. Here, subject is John, whereas predicate is a student. And the predicate logic representation is like this: student of. So, student is a predicate and John is a subject. So, it should be represented as an argument, which means that John is a student. Then second example, Mary runs. So let's break down the sentence. So here subject is Mary and predicate is runs. So it should be represented as runs in bracket Mary, and meaning is Mary runs. Then you can see sentences with relationship between entities. So again, with the help of this predicate logic, we can even represent relationship between multiple entities. So especially using binary predicates. So, if you take this example, John loves Mary, here subject is John, predicate is loves, and the object is Mary. So, you can represent this sentence in predicate logic as loves in brackets John, comma Mary. You can have any number of arguments, right? So, which means that John loves Mary. So, here predicate is loves. Then sentences with quantifiers. So usually quantifiers, they express generality or existence, and also they allows us to represent sentences with a broader scope. So these are two main types of quantifiers. So universal quantifiers, which represents for all, whereas existential quantifier, it represents there exist. So you will see universal quantification. Say the given sentences all students study. So first find out subject and predicate, and if there is an object, then that object as well. So here subject is student and predicate is study. So it should be represented as, so as is a universal quantifier, we need to use for all x, student of x derives studies of x, which means that for all individuals x, say if x is a student, then that student studies. Existential quantification. So here there exist, right? So some students study as a sentence. So break it down. So subject is nothing but student and predicate is study. So this can be represented like this: there exist x, student of x, and studies of x. So meaning is there exists at least one individual x such that x is a student, and so x should be a student as well as x studies. Lambda calculus is a formal system used to express computations based on function abstraction and application. It forms the basis for many functional programming languages like Haskell, and it is a tool for analyzing functions, expressions, and compositional semantics in linguistics. So, coming to the key components, first one is variable, which represent individual elements or parameters like x, y, z, and so on. So, all the individual elements. Then functions. So, these functions are derived using the lambda notation, and usually function takes argument, so that we all know. So, functions take argument and returns result. So, that can be written like this: lambda x dot e of x. So here lambda x, it introduces a function that takes an argument x, and this e of x, it is an expression that describes how x is transformed by the function. Let us see this example: John loves Mary. In this sentence, loves is a transitive verb that requires two arguments, subject as well as object. And in lambda calculus, loves can be represented like this. So, which means loves is a function that takes a subject x and an object y, and it returns whether x loves y or not. Then, step 2. So, we need to represent John and Mary. So, we can represent John and Mary as constants. So, John is represented with J and Mary with M. And step 3 is to combine the parts. So, in order to form the meaning of the sentence, John loves Mary, we should apply loves function to both John and Mary. So, what is loves function here? This one. So, you need to apply this to both John and Mary. And the result is true if the relationship holds. Coming to the applications of logistical semantics, first one is natural language processing. So, logical semantics they play a very important role in natural language processing, which involves using computers to understand, interpret, and generate human language. So, these are few NLP applications. The first one is machine translation. So, logical semantics they helps in translating sentence from one language to another language. So, say for example, if you take this sentence, every teacher loves every student. So, it requires understanding how universal quantifiers and logical relationships in one language correspond to the structure of another language. Then, coming to question answering, so they can even be used to understand underlying meaning of question. So, first, the machine should understand question, right? Then only it can extract the appropriate answer from the knowledge base. Say if the question is who is the president of France? The system must identify president and France as key predicates and entities to return the correct answer. The third one is information extraction. In text analysis, logical semantics is used to extract structured information from unstructured data. So, this unstructured data can be either an article, book, website. Okay, so it can be anything. So, why these logical semantics are used means in order to identify various entities, relationships, and properties from the data. So here we can take one example. Albert Einstein won the Nobel Prize in Physics in 1921 for his work on the photoelectric effect. So first information should be extracted, right? So this complete sentence is an unstructured data. So this logical semantics is used to extract structured information from this. So extracted information will be person. So identify person in the sentence. Person is Albert Einstein. Then find out award, Nobel Prize in Physics. Then year 1921 and the reason for award is photoelectric effect. So this information will be extracted. And second application is knowledge representation and reasoning. So even logical semantics, they are used for representing knowledge and reasoning in AI system, allowing systems to derive conclusions based on formal rules. Say in medical domain, logical semantics helps create an ontology that formalizes relationships like doctor, which is a type of who is a type of person, treats a patient. So if that is a sentence, doctor treats a patient, then these relationships can be used to answer queries like who are doctors treating patients with cancer, and even automated reasoning. So medical diagnostic system can reason about the conditions under which patient might be diagnosed with certain disease based on given symptoms. And this logical semantics formalizes the rules that relate symptoms to diagnosis, helping the system make informed decisions. Then coming to the third one, artificial intelligence and cognitive science. Cognitive science and AI also this logical semantics help simulate how humans understand and reason about language. So first example is natural language understanding. We are using voice assistants, right? So voice assistant like Siri interpreting Play a Song by Taylor Swift uses logical semantics to map the meaning of the request. That is the intention of playing a song by the artist Taylor Swift to specific action. That is, action is playing media files by a specified artist. So that mapping will be done with the help of this logical semantics. Then human like reasoning. So in AI based chatbots, logical semantics helps the system deduce answers from a knowledge base. Say if a user asks what is the capital of France, System uses logical semantics to reason that Paris is the capital of France based on the structured knowledge in the database. Then, in robotics and autonomous systems, if you take human robot interaction, so robot being instructed to pick up the red ball and place it on the shell needs to understand red ball as an object with specific color and shape and shell as a location for placement. Right? So logical semantics is used to disambiguate the instruction and translate it into action. In the same way, autonomous vehicles. So, if you take self driving cars, they even use logical semantics to interpret instructions and environment. Say, if the instruction is turn left at the intersection, so that sentence or that instruction must be understood in the context of the vehicle's position and the road layout. And logical semantics ensure system correctly understands the instruction and can make the appropriate decision.